So my name's Sylvia Sullivan, and I'm an assistant professor in chemical and environmental engineering here at the University of Arizona. I do atmospherically related research, so I also have a joint appointment in hydrology and atmospheric sciences. And I've been here now a little more than a year and a half. So I joined in January 2022, and I moved here from Germany. It was quite a move. Um, my trajectory started in Dallas. I'm originally from Dallas. I went to a high school that was kind of focused on science and engineering. In high school, I was very into chemistry. I loved like Bunsen burners and kind of, playing around with chemicals and stuff in the chemistry lab. And so when I went to college, I decided I wanted to do chemical engineering because I was good at math too. And I was like, God, I really love chemistry. So I did my bachelor's degree at Caltech in the Los Angeles area, and I studied chemical engineering there. And as I did that, my love for chemistry kind of waned a little bit, and I decided, what was more my passion was sort of, I guess, kind of applied math. I really liked using math to try to, model and understand things. And I really liked environmental work because I felt like it was very impactful, as opposed to just kind of synthesizing things in the lab, which was less my calling. So I minored in environmental science, and then I went on to grad school, staying in chemical engineering, but really kind of shifting my focus towards more environmentally oriented work. And I did my thesis on ice formation in clouds, so nucleation. And you can sort of think of a cloud as a control volume, and chemical engineers care a lot about flow in and out of a control volume and sort of phase changes and chemistry within a control volume. And so that's how we were thinking about clouds in my thesis. And we did modeling of ice formation in a couple of different frameworks. So I sort of became a cloud researcher and kind of fell in love with clouds because they're very beautiful, very poetic. And I also, I like that kind of natural poetry about the, natural world is very beautiful and poetic. And so that also had kind of appealed to me outside of the technical work. Yeah, and then I did 2 different postdocs. I moved around a lot. I moved up to New York City. I was really excited about going to New York City for a postdoc, and then realized that I was not a big city person. But the kind of academic path allowed me to move a lot and kind of, test sort of different fields and also different locations, which was really cool. So I spent a couple years in New York City, studying storms more than just clouds, kind of aggregations of clouds. So I was in New York City, and then I moved to Germany for 2 years. So I also got to live in Europe for a little while. And both of those were sort of positions that helped me contextualize cloud ice formation. So when I did my thesis, it was just sort of in isolation. And then these postdocs helped me sort of think about what does it mean, cloud ice formation in the context of climate. And so that is kind of what I'm building upon here at University of Arizona. And I was really excited about this position because it kind of combines my background in chemical engineering with the more environmentally oriented research. The U of A is one of the only universities, I think, that has a Department of Chemical and Environmental. So normally chemical is paired with biomolecular or bioengineering. So at the U of A, it's actually paired with environmental, which is really nice for me. And location, Tucson is wonderful, very beautiful. And I'm a runner and a cyclist, so I was excited about kind of being in this area. So that's what brought me here. And then, like I was saying, we are kind of building a research group then that thinks about clouds broadly, ice clouds more specifically, and how ice clouds fit into the climate system. So there are kind of 2 main prongs to that. Ice clouds have an energetic effect. So once they form in the upper atmosphere, then they are releasing latent heat when the ice crystals form, and they're also absorbing sunlight or outgoing infrared radiation. And so that latent and radiative heating changes the temperature gradients in the atmosphere, and that then affects circulation. So there is this energetic effect, but also ice clouds are associated with storms. So maybe you can kind of see in the picture behind me, not super well, but storms tend to have like a convective core. And then when that convective core gets high enough to temperatures that are cold enough in the atmosphere, then it starts to diverge. And so that diverging motion makes these very, very thick, what we call anvil, because they look like an anvil ice clouds. These sort of storm systems that are made up of the core and the anvil are responsible for really high intensity precipitation. And so we're interested in like what those anvil clouds look like, how the storms propagate, and that the anvil clouds would move with them, things like that. So broadly speaking, we are interested in the energetic and precipitation effects of ice clouds. And so we're very much using HPC in studying these climatic effects of ice clouds. We run very high resolution simulations, what are called storm resolving simulations, because the mesh that these models use is fine enough to resolve convective storms. In bigger climate models, then the mesh is so big, you know, you're looking at a grid cell which is 100 kilometers by 100 kilometers. And that's so big that like multiple storms could form within a single grid cell. And so now we refine that resolution and we're able to resolve the storms explicitly. And so HPC is very important in that, because when you run at those higher resolutions, then it's very expensive, computationally expensive, and the output volumes are huge. So you're talking about terabytes of data that are output even for small domains. Yeah, so I guess HPC is sort of involved in the whole workflow. Running the models is just the first step. When we get those terabytes of output, then we have to post-process them. And so HPC is involved in sort of using Jupyter notebooks or you know, visualization techniques on the back end to make sense of those output, you know, large volumes of output data. Yeah, and I guess there are sort of other components within the workflow where HPC comes into play too, like we're regridding the output data to different grids and things like that. Yeah, so HPC is kind of involved in all of our different pieces of what we're trying to do. And I think going forward, I'm interested especially in that kind of back end of the workflow. So I've been very focused in the past on running models and getting this very large output about clouds and different climate variables, because that in and of itself is quite labor intensive. But I'm becoming increasingly interested in, you know, how we make sense of what's being output. And there then we have ongoing effort to work with other visualization experts on campus and sort of think about how we might look at structures of clouds in different and novel ways, things like isosurfacing or kind of creating GIFs or animations of cloud and storm propagation. Trajectories, we're interested in kind of looking at flow in isolated parts of the cloud and storm systems. So there's sort of a whole zoo of things that we could do to make better sense of these very large data volumes that we're generating from these storm resolving models.